Our first half-century of space exploration, less than a human lifetime, has revealed that our solar system is truly a place of wonders. There are worlds beset with violence and dappled with oases of calm, worlds of fire and ice, searing heat and intense cold. Planets with winds beyond the harshest of terrestrial hurricanes, and moons with great subsurface oceans of water. In one corner of the Sun's empire, there are planets where lead would flow molten across the surface. In another, there are potential habitats for life beyond Earth. There are fountains of ice, volcanic plumes of sulfurous gases rising high into skies bathed in radiation, and giant gas worlds ringed with pristine frozen water. A billion tiny worlds of rock and ice orbit our middle-aged yellowing sun, stretching a quarter of the way to our nearest stellar neighbor, Proxima Centauri. It's very easy to look down, to not lift your eyes up to the sky, especially in a city like this. You never see the stars. You never see the solar system. So you can be lulled into a false sense of security. In a way, you could think that the Earth is just a stable place to be. And so that perspective that we've got since we began to explore the solar system, when we've begun to see, how unstable worlds can be, Venus is a good example. Venus, we think, was probably rather Earth-like in its early years, and then, because of a runaway greenhouse effect, has turned into this hellish world, as I referred to there, where molten lead would run on its surface. But it's a planet that's in many ways Earth's twin. I made this point that our exploration of the solar system may have made us seem small and in some sense insignificant. But in another sense, what we've discovered is that it's so astonishingly unlikely that a world as stable as the Earth will exist. The search for exoplanets began really in the 1990s, towards the time when I was beginning to make television programs. We started detecting exoplanets. We hadn't detected any beyond the solar system when I was an undergraduate in physics. The survey of planets beyond the solar system is now a real science, and that's changing dramatically. Now, actually, with the launch of the Webb Space Telescope in particular, we're going to be able to start analyzing the atmospheres in detail of these things, and looking for signs of water vapor, and also then, potentially, the golden scenario, which would be finding oxygen in an atmosphere. You find oxygen, the finger points to photosynthesis. So you can see biosignatures in the atmospheres of planets beyond the solar system, potentially, with the new instruments that we've got. It's kind of science fiction at the moment. But if you think about it, what would an industrial civilization look like? We know that changes the atmosphere of a planet. And the idea we're beginning to get to the point where we can analyze the atmospheres and therefore characterize the planets in such detail, even though they're tens or hundreds of light years away, is, to me, quite astonishing. Well, certainly, in terms of black holes, if you go back even a few years, the great question was something called the information paradox. Stephen Hawking initially brought it up and believed that if you threw information into a black hole, so, a hard disk or a book or whatever it is, then that information would be destroyed. So it would have disappeared from the universe. And you can see why, because black holes contain the end of time within them. There's this thing, the singularity, which is, in a very real sense, the end of time. So you throw a book, it goes to the singularity, it's gone. Stephen also initiated the study of how black holes radiate. They have a temperature, and they radiate away. And so the question became, what happened to that information? If the black hole isn't eternal, if it goes admittedly on very long timescales, it just disappears into radiation and there's nothing left, then is it the case that the information that you've thrown in is imprinted somehow in that radiation, or is it the case that it's been destroyed? For many years, Stephen and others thought it was destroyed. That's problematic. Profoundly problematic. Because if you destroy information about the universe, then you can't predict its future. It's called determinism. Right. So this idea is central to science, that information is conserved. It's not created or destroyed. And recently, in the last couple of years, we, I think to most people's satisfaction, have solved that problem, at least in a sense that people now agree that information is not destroyed, that it comes out in the radiation. But the actual interpretation of what those mathematical results mean is certainly not agreed upon, because it's bizarre. And so people are talking about wormholes connecting the interior of the black hole to the far distant Hawking radiation that was emitted, billions and hundreds of billions of years ago. People talk about something called the holographic principle, which is the idea that really it comes from the observation that the information seems to be in some sense stored on the black hole's surface, on the surface of the event horizon, and not in the interior. And in some sense, the interior doesn't seem to exist, certainly in some pictures. So all this tremendously advanced work on black holes and the information paradox has come about in the last few years. And I'm particularly interested in that at the moment. That was going right back to the first programs that I made 15 years ago. We touched upon black holes. But at the time, I think the richness of the description of them was just not apparent. When I made Wonders of the Solar System, which is the first big series that I made, we hadn't been to Pluto, for example. And now we've been to Pluto. So we see it. And, Pluto is a great example, actually. Because every time we go to somewhere out on the edge of the solar system, or even moons around the gas giants in the outer solar system, I think before we get there, we just assume that they're barren lumps of rock. It's just our basic assumption. It's like our moon, there's nothing much happening there geologically. And you go to Pluto, and you find out that it seems to have a heat source in its interior, probably radioactive. And we find a surface that looks new because it's not got very many craters on it. So people speculate about water, potentially liquid water, below the surface of Pluto. So Pluto becomes a place where possibly you could imagine life, microbial life, for example, in the same way that we can imagine it now on moons of Jupiter and Saturn, that we had no idea that these would be potential habitats before we went there. And I think that's key, really. Our imagination tends to be less vivid than reality. It's certainly been the case with black holes. As you say, now we have a photograph of a black hole. Now, I'm using photograph in the loose sense, it's a radio telescope image, but it's an image of a black hole at the center of a galaxy about 50 million light-years away. You go back, not quite 10 or 15 years, but a couple of decades, and there was still a debate about whether black holes existed. I mean, they're predicted by Einstein's theory of general relativity, but certainly before the war, the Second World War, people really didn't think they existed because they were too absurd. It was actually Arthur Eddington's comments on it, the great physicist. He said that nature would not allow things so absurd to exist, because the challenges they pose are so deep that you just think, well, it can't happen. And actually, it's people like Robert Oppenheimer, very famous for the Manhattan Project, who first showed in the late 30s that probably a star, with certain assumptions, could collapse without end to form what looked like a black hole. And then Roger Penrose got the Nobel Prize for that recently. So that was in the 1960s, they proved that, with very general assumptions, you would expect sufficiently massive stars to collapse. Even that, it's in my lifetime that people managed to prove, to most people's satisfaction, that black holes might exist. But it's not really till the 80s or 90s, I think, that you really start getting this really firm evidence. And then, only a few years ago, that we get an actual photograph of one of the things, a big one, by the way, 6 billion times the mass of the Sun. The idea that there are ripples in the fabric of the universe that we detect from black hole collisions primarily, or neutron star black hole collisions. I remember filming at LIGO, which was the gravitational wave detector, which subsequently, again, got the Nobel Prize for detecting them. And at the time when I was there, 15 years ago, I think, it was just a thing in a swamp in Louisiana. It didn't look like the sort of thing that would turn into the high-precision device that we've got now that's detecting, black hole collisions. It almost feels like every week, it's not quite, but, the idea that black holes are colliding out there so regularly, that every month or a couple of months we see the ripples in the fabric of the universe pass through the Earth and can detect them, is astonishing. And as I mentioned before, black holes, one of the most interesting things about black hole research is that it's telling us about the structure of space and time. What the black hole research is suggesting is that space and time are not fundamental, that they emerge from some deeper theory, some deeper structure in the universe. And it looks like that would be quantum entanglement or something like that. So it looks as if there are, you might call them atoms of space and time, or building blocks of space and time, which is really quite profound. Because you need to know that if you're going to really address questions about the origin of the universe, truly understand whether it had an origin in space and time, and if so, what was that like? Ultimately, you need a theory of space and time. And that's what Einstein's theory doesn't provide. General relativity, for all its power, takes as a prerequisite